The first talk today will be presented by Fabian Neumann, who is a PhD student in the Energy Systems Modeling Group at Karlsruhe Institute of Technology. He studies methodologies to improve power network representations in cross-sectoral decarbonized energy systems that co-optimize generation, transmission, and storage. And I will be playing his video, and then he'll be answering questions about his talk. So let me just... All right, can someone confirm they can see my screen?
Yes, looks good.
Thank you.
Hello and welcome to my talk on the near optimal feasible space of a renewable power system. My name is Fabian and I am a PhD student in the Energy System Modeling Group led by Tom Brown at the Institute for Automation and Applied Mathematics.
It looks like the volume is very low, I'm not sure.
But I thought I'd show my face at the beginning.
Does the volume improve?
We investigate the most cost-effective pathways to reduce greenhouse gas emissions in the energy system. And we do this by building large optimization models. In these models, we always consider the simultaneous investment planning of generation, storage, and transmission infrastructure all at once, because they are strongly interacting. This allows us to assess the many trade-offs regarding investment decisions. For instance, we can explore whether the model chooses to integrate large shares of renewables by balancing in-feed in space with transmission network reinforcement, or by balancing in time with long-term hydrogen or short-term battery storage. The overarching objective is to minimize the yearly system costs, which comprises both annualized capital costs as well as remaining operational costs, given a particular emission reduction target as a constraint. We moreover demand that energy demand is met at each node in each point in time, and we introduce transmission constraints between the nodes as well as multi-period linearized optimal power flow. This set of constraints moreover includes limits on the availability and potentials of renewables, which are derived from reanalysis weather data and land use databases. For both the spatio-temporal representation of available renewable resources and to see bottlenecks in the transmission grid, we typically run the optimization for hundreds of nodes and an hourly resolution for a full year in a single optimization problem for one set of cost parameters. Since we only include continuous variables and linear constraints, we can avail of the computational advantages of linear programming. So in this example here, we optimized the system for 100% emission reduction, where we consider only the power sector, a 200-node model of the European transmission system, resolved at a 2-hourly resolution for a full year. We optimized generation, storage, and transmission in a greenfield approach for the most part. The exceptions here are the transmission grid, hydropower, and run-of-river power plants. You can see that this system is very reliant on offshore and also onshore wind energy with a lot of transmission expansion in the system. Here, hydrogen storage pairs very well with onshore and offshore wind in the North Sea region, and solar, as you would expect, is the dominant energy carrier in the south of Europe. So is there a problem with this solution? It is, after all, the cost-optimal solution within the model boundaries. The answer is yes, because there's soft factors such as social constraints and public acceptance, which we typically do not model. The topic of this presentation is to look beyond this cost-optimal solution and see whether there are similarly costly but technologically very diverse solutions which might exhibit other favorable features. To illustrate how we obtain feasible near-optimal solutions, I brought a sketch. So here we have a decision variable, or this could also be a group of decision variables on the x-axis, and on the y-axis we have the objective function. And what we have done in the previous example is we have looked in the direction of the objective function for the cost minimal solution, and we obtained one optimal solution. However, there might be lots of similar solutions which are not that much more costly, but which are also within the feasible space. Now, having obtained this optimal solution, we add an additional constraint to the model, namely a constraint that defines what part of the feasible space is near optimal in terms of cost. And this constraint requires the objective function to remain within 1 plus epsilon of the optimal solution. With this constraint on the maximum cost deviation, we then vary the objective function and minimize or maximize a decision variable or a group of decision variables. Let me give you an example. We could allow a cost deviation of 5% and then minimize and maximize the deployment of onshore wind capacity in the system. This methodology is related to the modeling to generate alternatives methodology insofar that it allows a fixed cost deviation, but differs insofar that it has a more structural approach to going to the boundaries of the near optimal feasible space in terms of the search directions. That was already all of the methodology section. It's actually a very simple approach, but produces very insightful results. The only drawback is that there are a lot of optimization problems to solve, and one optimization alone can already consume a few hours and lots of gigabytes of memory. But luckily, we can avail of large cluster computing facilities. So without further ado, I would briefly lay out the experimental setup before presenting the results. First, we have to find the least cost power system, and then for many cost deviations from 0.5 over 1% up to 10%, we maximize investments in generation capacity, storage capacity, and transmission volume, such that the total annual system costs increase by less than epsilon. For the generation capacity, we consider onshore and offshore wind separately and also together, as well as solar PV installations. For storage capacities, we consider hydrogen and battery storage, as well as the total storage capacity. For the transmission system, we look at the volume that is comprised of the product of length and capacity. In the results that I will show, we look at the minimum and maximum capacities in the whole system, but this methodology works just as well per carrier and country. However, the per country results did not require a very deep analysis. In fact, any country could give up on one carrier completely because the neighboring countries can take up the gap. I want to start by illustrating how the results change on a map when we try to decrease the total transmission volume. What you see here is the optimal solution from earlier. So the epsilon is at 0%. I will increase the epsilon values to 1%, 5%, and 10%. And you can observe how the transmission expansion changes, the deployment of solar generation changes, and also the deployment of wind and hydrogen storage changes. So already as we go to 1%, we see a lot less transmission network expansion. Once we go to 5%, there's only very few lines that get expanded. Once we go to 10%, we also see that the solar capacities get more evenly distributed and move northwards to compensate for the lack of transmission system expansion. You see that the system composition is very different within a very limited cost increase of 10%, which you could say is very well within the normal error boundaries of our models due to cost assumptions and model simplifications. And this is quite significant. It means that there's a very wide range of feasible choices, and there are few must-haves or must-avoids. And we will look at this in more detail on the next slide. This slide shows the key results of our study, and we will spend some time explaining what they show. All these 8 subplots are structurally very similar. They show on the x-axis the cost deviation, ranging from 0 to 10% in steps of mostly 1%. And on the y-axis, the minimum and maximum installed capacities per carrier. We have a subplot each for wind, onshore wind, offshore wind, solar PV on the left-hand side, and storage and transmission infrastructure on the right-hand side. I want to draw your attention first to the 4 plots on the left-hand side, which are concerned about the generation infrastructure. We see that we require quite a lot of wind generation capacity in the system, even at a cost deviation of 10%. However, if we look at the onshore wind, there's some very interesting results. At a cost deviation of 4%, you can give up on onshore wind generation completely in the European transmission system. Obviously, this cannot be achieved without some compensation by offshore wind and solar PV. Offshore wind, on the other hand, is more essential to keep the system costs low. But also here, for a cost deviation of 8%, we can go without offshore wind generation completely. In terms of solar, we have a much wider picture, but it's also a bit distorted due to the different capacity factors of solar and wind generation. But what all of these share is a strongly nonlinear behavior, meaning that a small cost increase will already yield high flexibility. And within a 10% cost increase, there's little must-haves in terms of generation capacity. Let's now look at the transmission system expansion on the bottom second left to the right, where we see that even for a cost deviation of 10%, we need some transmission expansion. But also here we have some nonlinear behavior where for a very limited cost increase, we can forego a lot of the proposed optimal line expansion. Likewise, if we look at the storage expansion directly above, we see that we definitely need more storage than we currently have with our hydro and pump hydro storage capacities. The requirements of which are much more stable, meaning that they don't decrease that much when we allow a higher cost deviation from the optimum. If we finally look at what of the storage technologies, here hydrogen for long-term seasonal storage and battery storage for daily balancing, then we see that the long-term storage is essential for a nearly cost-optimal system, whereas the batteries do not seem to be so vital. So from this analysis, we get some rather vague but robust boundary conditions, which leaves lots of degrees of freedom to debate how the future energy system should look like. A criticism of this plot is that it doesn't show any interdependencies when maximizing or minimizing particular carriers. So when we minimize onshore wind, we don't know exactly what the responses in terms of investments for the other infrastructure types is. Because we're solving a convex linear problem, we only know that it must be within the shaded areas of each of the subplots. To conclude the talk, let me give a brief summary and an outlook. We had the goal to find a set of technology-specific boundary conditions for predefined cost decreases in order to depict the vast degrees of freedoms we have when designing cost-efficient future energy systems. In the results, we have seen that there's a very high variance, so high degrees of freedom, in the deployment of individual system components, both on a system level and on a country level. But we have also seen that either offshore wind or onshore wind with some hydrogen storage and some grid reinforcement is essential. What we will work on in the future is first improving the visualization of the dependencies and also look at more search directions. Second, we could repeat this analysis when we couple all the other energy sectors with the power sector. Third, while this study looked at the structural uncertainty of the optimization problem, we could work on including also parametric uncertainty of cost assumptions. If you have a further interest in the open source energy system model that we use, visit the GitHub repository at github.com/pipesa/pipesa-eur.
Great, thank you very much, Fabian. I can see that we have one question in the chat from Dan. It says, thank you very much for your presentation. How does your approach compare to parameter sensitivity analysis? For example, changing the cost of different generation resources, different amounts of load growth, etc. You could, for instance, characterize the set of optimal solutions as parameters vary via parametric linear programming.
Yeah, that's a very interesting question, and we have definitely already thought about this. So if you remember the sketch from the beginning, if you change the cost assumptions, you basically change the definition of what you classify as near optimal. And so these could work very well together, that when you run through, so you add another dimension, and in addition to the structural uncertainty, run through the parameter space of your cost assumptions. And then you could create these C-plots as somehow a, you could propagate the uncertainty of the cost assumptions to that by from your samples, yeah, where you have repeatedly done this MGA analysis for different cost assumptions.
All right, Dan asked another question. Could you compute the full set of extreme points that are in the feasible region that have a cost less than your specified threshold? Your current approach identifies some of the extreme points, but not all. I'm wondering if there's a simple way if there's a simple too many to compute all of them, or if it might be achievable. Could you then compute all Pareto optimal points?
Yeah, I think it's difficult, so that there are many dimensions, and the results I've shown, there were just sums of capacities in the whole system. What is an idea if you want to say combine or look at a two-dimensional plot where you combine solar and onshore deployment, and you go to the extremes in both of these orthogonal directions and find the extremes, then you could go basically to an extreme, the sum of solar and onshore wind. But yeah, this just massively increases the numbers of runs you have to do, basically.
We'll take one more question. You have two more, but I would recommend the next one go offline. Thank you very much for the presentation. Could you comment on how the cost distributions across countries and regions and allowing increased total cost affects the distribution?
So there's one set of cost assumptions for each carrier, and they are uniform across all regions. And the investment decision is just made based on the resource and how well it can be balanced at that location, if I understood the question correctly.
That makes sense to me, at least. If there's a follow-up, put it in the Q&A, and Fabian
Yes.
will be happy to answer it through the typed answer mode. All right, thank you very much, Fabian.